Procedural safety in aviation is built upon the reality of human neurological limits. A superior pilot integrates these biological parameters into their decision-making process, ensuring that safety is engineered by design rather than left to effort. This integration is the work of aviation psychology. It is an applied specialty used to describe, predict, understand, and influence behavior within the aviation community to improve safety and efficiency. To achieve those aims, we must identify the primary bottleneck in the pilot's information gathering phase, cognitive workload. Specifically, the heavy mental effort required to process complex data, like ATC clearances, through short-term memory. This chart details our memory constraints. Short-term memory has a hard limit of 7 ± 2 items, decaying within 10 to 20 seconds. We bypass this through chunking. Breaking complex instructions into 5 manageable blocks keeps data within the brain's processing threshold. Safe flight operations require that every cockpit procedure is engineered to fit inside this 20-second window. If the task exceeds these neurological parameters, the system of safety fails. Vigilance represents the active capability to remain sensitive to environmental changes above a specific threshold over time. It is a measurement of alerted capacity rather than a simple state of being awake. Monotony and fatigue degrade this capacity into hypovigilance, leading to reduced sensory perception and dangerous microsleeps. Pilots mitigate this through specific SOPs, including structured rest and proper nutrition. This spectrum maps the divergence of alertness levels. In contrast to hypovigilance, hypervigilance occurs during extreme panic. It results in indiscriminate attention to every threat cue, regardless of relevance, and leads to regrettable decision-making. The hypovigilant path leads toward complacency, a state of self-satisfaction paired with an unawareness of incoming danger. Automation often triggers this state by reducing the pilot's active workload to dangerously low levels. Optimum vigilance remains a fragile, narrow state. It requires active management to stay centered between the drift of monotony and the paralysis of panic. Pilots manage high workload phases using motor programs. These are behavioral subroutines, like flying a coordinated turn, which are learned through repetition and held in long-term procedural memory to be executed without conscious thought. This timeline details the Anderson model of skill acquisition. Developing these programs requires progressing through the initial cognitive phase, the connective associative phase, and finally the automatic phase. However, a sudden abrupt stimulus can trigger the startle reflex. This physiological response bypasses the central nervous system entirely, causing an involuntary body jerk and blink. This reflex creates a dangerous operational hazard, as it disrupts trained motor tasks for a window of 5 to 10 seconds. During this recovery period, the pilot is momentarily unable to execute autonomous skills. True proficiency is defined by surviving that 10-second physiological blackout. Training ensures that once the recovery window closes, trained skills regain control from raw panic. These 7 steps form the circular logic of dynamic decision-making. The process begins with problem recognition and identification, moving through analysis and selection before concluding with communication and feedback. Decisions in the cockpit are never static. Because the environment is constantly changing, a correct decision reached 1 minute ago may be catastrophic 2 minutes later. Maintaining accurate situational awareness requires neutralizing 6 specific interferences. These are summarized by the mnemonic SBF-EPI: stress, boredom, fatigue, emotional disturbance, poor communication, and interruptions. Communication is further degraded by expectation bias. This occurs when a pilot hears the specific clearance they anticipated receiving, causing them to miss the actual instructions provided by the controller. Situational awareness is inherently unstable. It requires constant reevaluation to defend against internal stressors and external cognitive biases. While technology aims to support the pilot, it creates a paradox. Automation rarely eliminates human error. It simply relocates the error to different, often more complex cognitive functions. These comparative flowcharts trace the evolution of the transport cockpit. From Generation 1 to Generation 3, we see additional layers of software and hardware inserted between the pilot and the flight controls. This evolution results in the peripheralization of the pilot. Manual workload decreases, but mental workload increases as the pilot shifts from a physical controller to a manager of complex interfaces, often leading to a sense of being out of the loop. To remain effective, automation must be human-centered. Systems must be designed to be accountable, subordinate, and predictable, functioning as a complement to human skill rather than a replacement for it. As cockpit complexity grows, the pilot's role becomes entirely focused on managing software interfaces and maintaining deep mental engagement with the flight path. Managing that engagement requires physical health. It is vital to distinguish ordinary tiredness, which a single night's sleep resolves, from fatigue. Fatigue is a cumulative, insidious result of long-term stress and environmental demands. These physical states are regulated by the circadian cycle. This internal biological clock, located in the hypothalamus, coordinates body temperature and hormone secretion based on light and dark cues. Alertness follows a predictable 24-hour curve. Human performance reaches its critical circadian low between 0200 and 0400 hours, creating a massive challenge for flight safety during night operations. Travel across time zones requires the body to resynchronize at a rate of 1.5 to 1.5 hours per day. Due to our natural biological rhythms, adapting to eastbound travel is 50% slower than adapting to westbound travel. Cockpit design further accounts for physical variation through anthropometry. Designers engineer the flight deck around an eye datum based on the central 90% of the population, specifically disregarding the lowest and highest 5%. Safe operations require accepting that biology is a constant. Maintaining safety means adhering to these physical dimensions and chemical rhythms without exception. The hard data of human performance defines our capability. While visual channels process up to 80% of all information, our maximum acceptable workload is capped at 60% of our available crew resources. Human reliability is similarly measured. Simple, repetitive tasks carry a base error rate of 1 in 100. Rigorous, disciplined practice can only reduce that rate to 1 in 1,000. Master your biological limits. Recognize the interferences attacking your situational awareness, and trust engineered procedures over raw instinct. Human error is an inevitability of our biology, but in the modern cockpit, reliability is an engineered outcome.